Hello everyone, my name is Harshita Soner. Today we will discuss a topic of operating system, that is process synchronization and IPC. So first one is module 1. Here we will discuss the basic concepts. Introduction to process synchronization and its significance in multitasking environments. Let's see this diagram. Here resource 1 is assigned to process 1 and process 1 is waiting for resource 2, and resource 2 is assigned to process 2 and process 2 is waiting for resource 1. So this is the condition of deadlock. Process synchronization. What is process synchronization? In operating system, multiple processes run simultaneously. When they share the same data or resources, their execution must be coordinated to prevent conflicts. So why do we need it? Without synchronization, shared data can become inconsistent. Synchronization ensures that concurrent processes cooperate and access shared resources in an orderly manner. So what is the critical section problem? Critical section problem is a part of the program where processes access shared resources like variable, file or database. What is the conflict here? Only one process should be in critical section at a given time. No other process can enter in critical section if already one is there. What is the goal of critical section? Its goal is to design a protocol that allows processes to cooperate without interfering with each other's data. Solution requirements: mutual exclusion, progress, and bounded waiting. So, what is mutual exclusion? If one process is in its critical section, then no other processes can enter its critical section. Then what is progress? If no process is in critical section, then the decision to enter cannot be delayed indefinitely. What is bounded waiting? There must be a limit on how many times other processes can enter before a waiting process can get its turn. So what is race condition? Race condition occurs when multiple processes access and manipulate the same data concurrently. The final outcome depends on the order in which the access takes place. This can lead to unpredictable and wrong results, just like two cars trying to merge into the same narrow lane at once. Synchronization hardware. Atomic instructions. Modern CPUs provide special hardware instructions that are atomic. Test and set. An instruction that reads a value and set it to true in one signal and non-stop step. This can be used to build simple locks. Then what is swap? An instruction that swaps the contents of two memory locations atomically. Effect. Hardware level solutions are very fast but can be difficult for programmers to use directly in complex applications. Introduction to semaphores. So, what are semaphores? Semaphore is a powerful tool used to manage synchronization. Think of it as a signaling system similar to a railway signal. It is basically an integer variable that processes can access only through two atomic operations. First is wait and then signal. What wait does? Decreases the value. If 0, the process must need to wait. Signal. It increases the value. Signals that resources is free. Semaphore implementation. To avoid busy waiting, we use a blocking mechanism. Block operation. If a semaphore is unavailable, the process is suspended and placed in a waiting queue. Wake up operation. When a process releases the semaphore, it signals the OS to wake up one process from a queue. Here is the binary versus counting semaphores. What are binary semaphore? Binary semaphores act like simple locks. Counting semaphore are used to manage multiple multiple instances of a resource like a pool of 5 printers. Here is the diagram of value range resource management complexity. Module 2. Classical IPC problem. Standard synchronization problem used to test every new synchronization primitive or logic. Bounded buffer problem. Producer and consumer. One process creates item and puts them into a buffer. Another process takes them out to the process to them. The problem. The producer should not add to full buffer and the consumer should not take from an empty one. Reader writer problem. So what is it? Here scenario is multiple readers. It is allowed because reading doesn't change data. Many people can read at once. Okay. Then the scenario is reader and writer not allowed because a writer might change the data while reader is viewing it. Here the scenario is multiple writers not allowed because two writers might overlap and corrupt the data. Synchronization must ensure that writers have exclusive access to the data. Dining philosopher problem. So, what is it? Five philosophers sit around a table with five chopsticks. To eat, they need two chopsticks, one left, one right. Deadlock. If every philosopher picks up their left chopstick at the same time, nobody can ever eat. The lesson this problem teaches us that about resources, allocation, and how to avoid system deadlocks. Thank you so much.